So group 2, I don't know if this is y equals the same over the same. In other words, it can be a line over a line or a parabola over a parabola. And we're going to look at the special things that happen in this situation. So I'll get you to copy those down, and while you're copying them down, I'm going to get you to add in red pen, hopefully you have a red pen, the asymptotes at y equals 3, x equals 1. Here this one has y equals 1, x equals 2, and x equals negative 2. Y equals negative 2, and x equals 1. In group 2, where it's line over line and parabola over parabola, the key characteristic and the key thing we'll have to figure out is the horizontal asymptotes. So once you've done copying it down, you have to see how you can tell from the equation where the horizontal asymptotes are. We already know that vertical asymptotes happen when you factor and a non-permissible value doesn't go away. But where do these horizontal asymptotes come from that are new? I'm going to actually add a word. You know how I have same over same? I'm going to add the word same degree, same degree. And it's a word probably you haven't heard much since grade 9, but the degree of something is the biggest exponent. So a line over a line would be a degree of 1 over a degree of 1. A parabola over a parabola would be a degree of 2 over a degree of 2. We could do this also with x cubes over x cubes, but you won't get that on your exam. They tend to keep things to lines and parabolas. The odd time they might give an x cubed. And we'll look at that a little bit, but not very often. So, the first one in group 2. The horizontal asymptote is at y equals 3. How can we tell right from the equation that it's going to be 3? There's a hint in the equation. The second one, it's y equals 1. There's a hint in the equation that it equals 1. And then I'm going to give you one more to try to really see if you really see the hint. Okay? I'm going to give you an equation. I'm going to make it a parabola. I'm not even going to write it in the right order. And I'm going to give you this one, and I'm going to tell you it has a horizontal asymptote at y equals, and I think once I tell you this one, you'll really see the pattern of how to tell where the horizontal asymptote will be. The answer to the last one is that it has horizontal asymptote at negative 7/13. And there's a hint in the equation to tell you that. Right? Sometimes using really obscure numbers like this really gives away the hint more than the other ones did. So now that you see the hint in the last one, can you see that that hint helped you in the first one, the second one, and the third one? Okay. So in the last one, well, there's a negative 7 in front of the x squared, and there's a 13 in front of the x squared. That's the highest degree, right? If it's same degree over same degree, you look at the highest one. So for x squared, you just look in numbers in front of x squared. If they were a line over a line, well, like the first one, you look at the number in front of x and the number in front of x. You see that you would have 3 over 1, which you just have to write as 3. The second one, the biggest degree is an x squared. You have 1x squared over 1x squared. It's equal to 1. And in the third one, you have a negative 2x over a 1, which would just give you negative 2. But it's important that you consider the number on the top and the number on the bottom. That's why I added that extra question, so you could really see it with the negative 7 and the 13. And the reason for this is as follows. Horizontal asymptotes tell you what's happening at an extreme. So, really big values of x. If I have 3x over x minus 1, and my big value of x is 1,000,000, what's the top of that fraction close to? Or what's it equal to? If x is 1,000,000 and you have 3 x's, it's going to be 3,000,000. Okay? What is the bottom of the fraction close to? Or what is it? I mean, I could ask you what it's equal to. You'd be like 1,000,000 minus 1. Well, no, tell me the number. You're like, well, it's close to 1,000,000. Right? If you had $1,000,000 and you lost one, would you be sad? Probably not. If you have just the right bus fare to get home and you lose $1, now we have a problem, right? But when things get big, it's not as much of a problem anymore. It's like, I don't know if any of you have ever played Monopoly. You ever played the game of Monopoly? Right? At the beginning, if someone lands on yours and you owe me $6, give it to me. And at the end of the game, if you've got hotels and they land on that same one and it's just boring $6, you're like, forget it. It's so little now at the end of the game, it doesn't really matter. So when things get really, really big, whatever is less than that degree really doesn't matter. So you basically have, ignore the minus 1, it's close enough to 3x over x. Here, x squared and x squared, the minus 1, the minus 4, when numbers are huge, it's not going to make much of a difference. So you just have x squared over x squared. And even in this one, even if x is big, like if I put 1,000,000, this is like 6 times 1,000,000. That's a big number. But it's not that big when you think of 1,000,000 squared. It actually doesn't matter. If someone had $1,000,000 squared and they lost 6,000,000, they actually, it doesn't bother them too much. Who's someone who has a lot of money and who's lost a lot of money lately? Anybody know? Elon Musk, right? His Tesla stock, boom, plummeted, right? I would feel really sad right now if in the last couple of weeks I lost hundreds of millions of dollars. No, I haven't. I don't have to get that first. But for someone with billions and billions of dollars, it's sort of like, well, it sucks, but it's not the end of the world. That's the idea of horizontal asymptotes in group 2. And the horizontal asymptotes only change in group 2. Notice group 1 had no horizontal asymptotes. Sometimes it had diagonal ones, but group 1 never has a horizontal one. Group 2 has horizontal ones that change depending on what they are. And now we're ready for group 3. And there's 2 sets. I'll let you copy these ones first. And we'll add the asymptotes. But group 3 can be described as, they're all, maybe I'll write it this way. Last one was same and same. This is smaller degree on the top, bigger degree on the bottom. So they're usually a line on the top and a parabola on the bottom. A bigger degree on the bottom. And this has an interesting situation that happens. It's really predictable. y equals 0, y equals 0, y equals 0. So take out your red pen and draw the asymptotes in. And the main characteristic of group 3 is that you always have a horizontal asymptote and it's always at y equals 0. Really boring. Group 2, the horizontal asymptote can move. Group 3, boring. All well, not boring, easy. Always at y equals 0. You can start it early if you want. So group 3, you recognize group 3 when you have a bigger degree on the bottom. In other words, there's a parabola on the bottom and a line on the top. And the line on the top can either be like mx plus b, like these ones are, or in these last ones, right? Sometimes the line can just be a horizontal line like y equals 6 or y equals 2. So as long as the degree is bigger on the bottom, the main characteristic is that you have a horizontal asymptote, but that horizontal asymptote is at 0. And I guess technically you could use, like, no one would ever do this. But you could kind of think of it like group 2. There's no x squareds on the top, right? So I could rewrite 6 as 0x squareds plus 6, and then, just like group 2, say, well, I know that my horizontal asymptote is whatever the numbers are in front, and you would get 0 over 1, which is 0. But it's much easier just to remember that if the degree is bigger on the bottom, you will always have an asymptote at y equals 0. And then with that in mind, why does that happen? Well, remember that horizontal asymptotes deal with extremes. And if you have a bigger degree on the bottom and you put in a huge number, does it make sense that the bottom is going to be huger? I don't know if that's is that an English word? Huger than the top? Bigger is probably, I like huger. More gigantic-er? No. I don't know if that's an English. Gigantic-er? Gigantic's a big word, right? Huger is better. So like here, If I put in 1,000,000, the top is 2,000,000. But the bottom is 1,000,000 squared, which is huger, bigger. And if it's bigger at the extremes, that means your graph is going to get closer and closer to 0. Right? Even just check 10. That'll give me 20 over 100. That's already 0.2. That's already fairly close to 0. And we only tried x as 10. And the last time I checked, I didn't feel like 10 was like a very, very big number. Right? 10's like a very big number if you're 7 years old. And you're like, oh, when I'm 10, those kids are so huge. Next, weird thing about horizontal asymptotes as compared to vertical asymptotes. Vertical asymptotes happen at non-permissible values. And your graph can never, ever, ever go through a vertical asymptote. But horizontal asymptotes just tell you stuff at the extremes. And sometimes, like this graph here, sometimes the graph goes through a horizontal asymptote in the middle. That bothers you a little bit because you're probably used to vertical asymptotes being non-permissible values. Horizontal asymptotes aren't non-permissible values for what? Horizontal asymptotes tell you what happens at extremes. But in the middle, like in this one, the graph went through the horizontal asymptote. So that feels a little bit weird. So now what we have to do is we have to say, okay, how do I take all of these characteristics, right? Group 1 was a degree is bigger on the top. So this was our parabola over a line. And our characteristics were sometimes there was holes. You're going to find out there can be holes in any graph if you wanted to. Okay? But sometimes this one had the oblique or diagonal asymptotes. This one never had horizontal asymptotes. And we found out that graphs have holes when you divide out something and it cancels. And what I mean that any graph can have a hole, I can go to, let's go to group 2. You can put holes in graphs if you want to. Like, this first graph is 3x over x minus 1. That is the correct graph. But I can add an x minus 5 on the top and an x minus 5 on the bottom, which would basically cancel out and not be there. But if I add it and cancel it out, I would add a hole at 5. You can add as many holes to a graph as you want. As long as you have the factor non-permissible value cancel out on the top and the bottom, and you're like, here's a graph with 30 holes. I can imagine on the exam. Can you imagine they just have a super long graph, 30 things cancel out, and you have to put all of those holes in your graph. They shouldn't let me write the final exam. I would get creative. I'd be like, this would be fun. And then everybody would be like, no, Mr. JR, don't make the exam fun. Yeah, so even group 3, right? You see how this is like a nice little speed bump graph? Right? If you want to put a hole in the top, just put an X on the top and an X on the bottom, which would cancel out, but then you have a non-permissible value of 0, you put a hole in your graph. So any graph can have holes. And a hole happens when a non-permissible value that is in the original equation goes away once you simplify.